Hi there, everyone. My name's Ross Walton, and I am the Senior Application Scientist at Unchained Labs. It's my pleasure to be your moderator for today's seminar, and I want to thank all of you for joining us. We're going to have a Q&A session at the end of this presentation. To ask questions, all you have to do is click the Q&A button in the Zoom navigation bar that's going to either be at the top or at the bottom of your screen, and then just type in your question. When submitting a question, please avoid clicking the anonymous button, so that way, if we don't get to your question, we're able to reach out via email and answer it. We'll get to as many of the questions you guys have as many of the questions you have during the live Q&A session. So first off, now I'd like to introduce my friend and colleague, Andre. He's the product manager for Aunty and for Honeybun at Unchained Labs. Today, Andre is going to be taking us through a brand new instrument that Unchained Labs just launched called Aunty. He'll be showing us how to set up, run, and analyze data from Aunty's TM and TAG experiments, and also from its colloidal stability experiments. You'll get a peek at the highest resolution stability data you've ever seen from 96 samples at a time. Plus, everything about Aunty is automation ready. So with all that in mind, and without any further ado, I'd like to hand things over to Andre. Hey, Andre, how are you doing?
I am doing very well. Thank you for this introduction, and I am very excited to tell the world in this forum about our new tool, the queen of protein stability. Let me set up my screen share here. And Ross, can you confirm that you see my slides?
Yep, everything looks good on my end. Take it away.
Perfect. All right. Well, again, thank you very much for joining me here this morning, this afternoon, this evening, depending on where you are on the planet. I am excited to show you all about Aunty, the queen of protein stability. At Unchained, we have always been, and we still are, and we will be, about providing the right tool for the job. If you see this image and you think, well, a screwdriver would be better, you are right. When you look at protein stability or the world of protein stability and the characterization of protein stability, there are lots of hammers, lots of screwdrivers around, lots of crude tools, lots of more sophisticated tools, but nothing really matches the throughput requirements of a modern biophysics, biopharma lab. And this is why today I am excited to tell you about the fully automated push one single button to screw down your protein stability high throughput screw gun. And that is, of course, our Aunty, the queen of protein stability characterization. We can look at all aspects of it. We can look at melting stability in the thermal gradient, look at the onset of melting and the half point of melting, TMs and the T onsets by fluorescence. We can look at the aggregation of our sample, the T-ag, the T-size. T-ag is, of course, based on SLS, T-size being based on DLS, and we can look at the colloidal stability to make predictions about long-term behavior. Look at the KD, the diffusion interaction parameter, the B22 second viral coefficient, or if you're looking at higher concentrations of proteins, we have access to the G22. These will predict the colloidal stability, the long-term stability, but we can also measure this directly in Aunty, and I'll talk and show you some data about this in the course of this presentation. If you're working with viral vectors, AAVs or adenovirus, you can also use, of course, viral vector stability to see how accessible the payload may be in a thermal gradient. So all of these protein stability metrics are accessible by measuring your sample in Aunty. And how does Aunty do all of this? It does it by combining three things: extremely high throughput with full spectrum fluorescence detection and best-in-class light scattering. Let's look at all three of these in turn. Throughput, we are measuring samples in a 96 SPS format plate. The samples, 8 microliters of sample, are held in an all-quartz well for optimal chemical compatibility and also, of course, stellar optical performance. This entire 96 well plate will be read every single minute of your experiment. And on and on and on until you have all the data you might want. And the system is automation ready. If you're using a 96 well plate, of course, that has automation readiness written all over it. We also have an API to control the instrument, and the tray that holds the samples comes out, so it's easily accessible by a plate gripper. So throughput, check. full spectrum fluorescence is very important to be flexible in characterizing your proteins. You can look at the intrinsic fluorescence, you can look at reporter dye fluorescence. No matter what your protein prefers or what you prefer to characterize your proteins, Aunty has you covered there. We excite fluorescence using LEDs. We have a 280 nanometer LED that excites, of course, the tyrosines and the tryptophans, the aromatic residues in the proteins. And we can also use a blue 470 nanometer LED to excite a reporter dyes like Citro Orange. Or if you're working with membrane proteins, CPM. We can measure the emission of the entire spectrum from 250 nanometers to 750, so nothing, no information escapes you. Aunty has it all under control. For our light scattering optics, we use a 660 nanometer red laser to excite fluorescence. The red laser is advantageous because there's nothing really that absorbs at that wavelength anymore in biomolecules. And we're characterizing the SLS and the DLS in parallel, detecting everything with a super sensitive avalanche photodiode. This way, we can catch aggregates as they form, and we can also tell their size as they are clumping together. Aunty, great. Everything brings all these things to the table, but the crown jewel of Aunty, really, the crown jewel of the queen is the plate. So again, a 96 well all quartz SPS format plate. You can see here on the left side, I've put in a multi-channel pipette with 8 channels. The spacing of the wells is the same as in a 96 well plate. We have 8 rows. We have 12 columns across. The wells themselves are interleaved, so we make ideal use of the space. The sample is pipetted in there, flows in really easily. You can do this manually with a single channel pipette, or you can use the multi-channel pipette. You can also use a pipetting robot, of course, to load your samples. And then when the sample is in there, we seal it. That way, the sample stays in the well, even in a temperature gradient, and contaminants stay out of the well. No worries about that. And then again, of course, the entire plate can be read every minute. Now you wonder, how do we seal it? Let me show you a brief video to illustrate this. So we start this off with the plate in white light, and then I will turn on black light and load some fluorescein and water to show you how easy it is to load. And then the application of the sealing strip works. So here you place the strip on, the seal on the sample, press it on. The black material you see is actually pressure sensitive adhesive. The seal material itself is Teflon, and you place it on, run over it with a spatula or with your finger, and that way sample is sealed and you can go ahead with your experiment. There is no film in the center where the wells are, where the measurement happens. So the only thing standing between your sample really and the optical system is a thin layer of quartz. And of course, quartz is optically stellar in its performance. We also do not have any adhesive applied where the input well is, so that if you were using a partial plate, you could load your sample, you could run an experiment and then remove the seal, load other wells, a single well, a single use, but you could use the plate, of course, multiple times. And I've only sealed 1/6 of the plate here. The seal comes in a full plate format. You can apply it to all of those. This is completely, you're flexible in doing this, whichever way works for you. Now, when your sample is loaded into the plate is sealed, ready to go. Your experimental setup is super easy. I have another short video here. So we're going to set up a new experiment. We choose our application type, application subtype, go next, name our experiment. Really simple, really light software interface. We can then select the wells that have sample, or if we don't want to select them one by one, we can load an Excel sheet with the sample information. We can set our temperature gradient in a thermal ramp experiment. We can set our parameters for data acquisition. We run through a summary of all of it, hit start, and then the experiment is off to a good start, and we gather all the stability data we want from your samples in Aunty. What does the data that we obtain look like? Here is an example of fluorescence data. So on the left y-axis, we plotted the BCM. This is an overlay of 8 IgGs that we run in this experiment. And you see the data is highly reproducible and really well resolved. We find from the BCM curve, we find the melting temperature by looking at the differential, finding the inflection point by looking at the local maximum. And that is how we call the onset, the midpoint of melting. Of course, on the molecular level, the fluorescence of the protein changes in a temperature gradient because the aromatic residues, tyrosine, tryptophan, that are normally on the inside, as the protein melts, get in contact with the aqueous environment, and that changes their fluorescence behavior. And then by following that over the temperature gradient, we can say when the melting has progressed halfway. we record this, and simultaneously with this, we record the static light scattering. And static light scattering is, of course, going to give us information about the increase of molar mass. As something aggregates, the molar mass will increase. Our resolution is a delta of 15 kilodaltons, so sensitively detecting aggregates as they form. And we have really nice and flat SLS baselines. And then we see that around, 69 degrees here in this case, is when that curve leaves baseline, and that's when we call the onset of aggregation. And we get these two things in parallel: fluorescence information about the melting and the SLS about the aggregation. Fluorescence about the melting and the SLS about the aggregation, and we can put those two into context. And what we can do also is, of course, use that the light scattering optical system to capture DLS information. And that gives us not only when is the molar mass increasing, but how big is it? What is the size increase? Really gives us access to the hydrodynamic size increase of our sample in our thermal gradient. And we can then also read up how big are these aggregates as they form. So melting, aggregation by molar mass increase, and aggregation by size increase, all of these things we can capture together. And it is really important to get this information about your sample in parallel all at the same time, so your sample is treated in the same gradient. Here in this example, that whole story is for trastuzumab in formulation 1 on the left, formulation 2 on the right. And you can see that in formulation 1, trastuzumab has one single melting event and one aggregation that is correlated to that. In formulation 2, had some more sodium chloride in it, we see two distinct melting events. The two domains of the protein seem to be melting at different times, or different temperatures, I should say. And only the second melting is associated with aggregation. So by knowing that full picture of melting and aggregation at the same time in formulation optimization, you know what screws to turn on and how to optimize the formulation of your analyte. The data that comes out of Aunty really comes out at warp speed. If 96 throughput is not enough, if you need to push your data, the read of data acquisition, or if you want to go through even more samples than a 96 well plate gives you, you could run your sample at 2 degrees per minute. What I showed you before was all at 1 degree per minute, kind of a standard setting. But if you wanted to go faster, you could set that thermal gradient more steeply and run through a ramp. In this case here, it's 20 to 90 degrees. So spanning 70 degrees at 2 degrees per minute, this experiment will only take you 35 minutes. This is adalimumab, and we see two nicely resolved melting events. And then this is a very aggregation, stable protein aggregation at 87.5 degrees about. And all of this data is acquired in only 35 minutes, including loading the plate. You're going to be done in under 45 minutes for 96 samples. So really nothing standing between you and running through all of these experiments, all these replicates. You have a great tool in Aunty to get through as much information, as many samples as you need. Full spectrum fluorescence is really relevant if your protein does not show any intrinsic fluorescence, or if you're doing anything outside the protein intrinsic fluorescence application. Here in this case, left side panel shows a TM of IgG using Cipro orange or reporter dye. We can call melting events there, of course, as well. Look at aggregation too. And on the right side, we get information about, if you're working with an AAV, at what temperature your AAV is losing its payload before the capsid itself falls apart. And you see there's a delta here of 15 degrees. So if you're working with AAVs, knowing that payload ejection is really a crucial metric in judging the stability of your AAV. The ability to measure the full spectrum of emission and excite fluorescence at 280 and 470 nanometers really keeps you as the experimenter flexible, and Aunty lets you use reporter dyes if you so choose. Colloidal stability, I touched on this at the very early stages. Colloidal stability is a predictor of how a sample will behave over longer periods of time. We're looking at the behavior of a sample, the light scattering behavior of a sample in a temperature, in a concentration series. And what we look for is really positive slopes. So the KD, the diffusion interaction parameter, if that is a positive value, as it is here in formulation green, that indicates that the sample is self-interacting repulsively and is stable over longer periods of time. In formulation blue, we have a slightly negative KD, which indicates attractive interaction, which would mean the sample would aggregate, and then potentially precipitate and not be as stable as it is in formulation 1 in green here. The nice thing in Aunty is that you can run this experiment at a given temperature, and then sample is in the plate. It's a non-destructive measurement, repeat the measurement again at a different temperature. So the entire range from 15 to 95 degrees, that's Auntie's temperature range, is accessible to your KD experiments as well. We capture the KD, the B22 and the G22 experiment data in parallel, so you can get all of these metrics covered and get all the information about colloidal stability that you need. Long-term testing or accelerated stability testing or storage testing is something that people normally put off till the very end of their development of a new candidate, because you need a lot of time and large sample volumes. Now, in Aunty, you can access this with only 8 microliters of sample. And here in this case, we look at an IgG that we stored at 62 degrees Celsius over 15 hours. The left panel looks at the protein and looks at the fluorescence, so a metric of the protein unfolding, and we can see that the unfolding proceeds more quickly in formulation blue than it does in formulation green. In the right panel, we're looking at the light scattering data of this IgG over 15 hours at 62 degrees, and the triangles are SLS here and here, and the diamonds are our DLS information. You can see that formulation blue formulation green leads to aggregation to a much higher degree than formulation blue. The green formulation, after 1.5 to 2 hours, you already have significant amounts of aggregates in there. And if I tell you that formulation blue used some arginine, you wouldn't be surprised, because arginine, of course, destabilizes conformationally, but stabilizes colloidally. So this information can be obtained right by incubating the sample in Aunty, or we also have our so-called out-of-the-box experiments, which means you will read your sample, you incubate it externally in an incubator at your given temperature, keep the instrument free for other experiments, and just bring the sample in to read another data point and append your experiment with point by point at any time point of your choosing. So the flexibility of Aunty and bringing all of these information streams, fluorescence and static and dynamic light scattering together, really is the strength here. I mentioned the automation readiness of the system. Also for the data analysis, we are geared towards looking at several experiments at the same time and increasing your sample throughput this way. We can open up to 4 experiments in parallel, and since each of the experiments is 96 samples, so up to 384 samples, we can plot whatever metric we want here on the X and the Y axis. There are little drop downs. Here I looked at TM as a function of TAG. You could look at the TM1 as a function of TM2. Any metric there is, you can plot this here, and then you can just lasso around the samples that show the profile that you're most interested in, and then go deeper in, take a deeper dive into the data and look at how do the individual spectra of these samples look and how do they compare to one another. So built into the software is already a very straightforward way of analyzing several experiments and drawing the right conclusions easily and smoothly. With all of this together, Aunty is the queen of protein stability. We are measuring stability in a 96-well plate, and we're doing this at breakneck, unprecedented speeds. Aunty works, of course, together with her court, with the other Unchained Labs biologic characterization tools, use Unagi for buffer exchange, use Stunner for quantitation and sizing. Viscosity is the domain of the Shining Knight honey bun. And then lastly, of course, Aunty gives you access to all aspects of stability. And I think you'll be as excited as I am using this instrument, because it is really fun to load a plate and to see all that data pour in at warp speed. Thank you very much, and I am looking forward to answering your questions.
Fantastic. That was a great talk, Andre. I think we've all learned a lot. So, you took us through how you can use Aunty to get stability data from 96 samples per minute, how you can power through thermal melting and aggregation experiments, how you can analyze SLS, fluorescence, and DLS measurements in parallel from a full plate during a thermal ramp. And also, it's really cool that you can compare 384 samples at a time within Aunty's software. I know that people are often using that sort of format to do measurements and to do comparisons. And so the fact that you can have all that data together in one place, look at all of it together, is a fantastic thing. So we've got a bunch of people who've already submitted some great questions. And I wanted to let everybody know that before we start the Q&A, if you're in the audience, you can still ask questions. All you have to do is enter them into the Q&A section of your Zoom bar, and we'll be able to get to them. All right, you ready for the first the first round of questions, Andre?
Of course, of course.
Okay, so we got this one. What is the lowest and also the highest sample concentration you can measure in Aunty?
Okay, yeah, sure. For fluorescence, our range of detection, and this is of course based on trastuzumab, so on an IgG, typical IgG. For fluorescence, we can go from 25 microgram per milliliter all the way to 300 milligrams. So 0.025 milligram to 300 milligram per milliliter of an IgG. That is the fluorescence range. For our SLS, it's 0.05 to 300 milligram per milliliter. And for DLS, it's ISO compliant DLS, so zero point 0.1 milligram per milliliter lysozyme, or equivalent is our DLS LOD.
Gotcha. Thanks very much. Okay, and then so what kind of 96 well plate are we using? Is it, a plastic? Is it quartz? And then what's the advantage of using the material?
Yeah, no, of course. So when we developed the instrument, we found that there's not really any consumable out in the market that would give us the performance that we need. So we built it ourselves. So this is it's a Unchained Labs made 96 well consumable. We have the chips, if you want. The wells that are in there are all quartz. So it's a three-layer structure of quartz that we make, and then they're placed on a plastic grid in the SLS format, and we provide you with the plates and with the plate seals, and then you can load your samples, 8 microliters of each, and go for it. Quartz again is, from its chemical compatibility properties and from its also optical properties, of course, the best system to look at all the fluorescence and all the light scattering data you need. And we tried other things and nothing matches quartz. So we give you the plate, we provide you with the plate you need for Aunty.
Gotcha. Thanks very much. I think you answered this during talk, but can the system be automated?
Yes, the system can be automated. Again, the tray of the sample or the sample holding tray comes out of the system, so it's easily accessible by a plate gripper. We can load the plate using a pipetting robot. We can also control the system with an API, so the system is automation ready. And one thing I did not talk about in the actual presentation is we also, of course, can export the information in a spreadsheet format if you wanted to use it in other applications downstream.
Gotcha. Okay, cool. So are the consumables single use?
The consumable is single use on a per well basis. So a well is designed for single use. You are basically denaturing a protein in there, so there's no way of getting anything out. You can use the plate multiple times, but every well only once. So say you run 16 samples today, you could run the other 80 tomorrow. We have the seal, as I showed you, is perforated, so you can easily separate the seal into different strips for the individual chips and use it that way. And the plate can be used multiple times, but the well is single use.
Cool. Can you measure fluorescence, DLS, and SLS at the same time?
Yes. We can measure SLS, DLS, and fluorescence at the same time. We are using two distinct optical systems. As the sample, as the optical system sweeps, or as the plate moves under the optical system, we measure them in parallel. It's the co-localized SLS and DLS at any experiment, anytime you want. If you don't want it, you can, of course, disengage one of them, but you gather all of this data throughout every point of your experiment.
Very cool. Does the seal interfere with the measurements?
The seal does not interfere with the measurements because there is no seal where the measurement happens. So the seal has this oval center piece that is open, so that where the actual wells are, where the experiment happens, where the excitation and the emission is being recorded or happens, there's nothing in between your set. It's just a sample and a thin sheet of quartz, and then you have the optics. So the seal really is only at the vent holes and at the input ports to make sure that the sample stays in the well, but it does not interfere with our measurement.
Fantastic. So here's one that's kind of interesting. Can you check if folding is reversible? So it would be there a way of, doing a ramp up and a ramp down and monitoring things
Yes.
as that happens.
Yes, of course. You could do that. We have a free-form application that lets you design whatever experimental type you want and choose whatever metrics you want to record in any aspect of your protein, if you experiment. So you could set it up very easily, and this is mirrored image. So you could really set it up to have a temperature, spike up, read, spike down, and see how much is the fluorescence recovering. So that is definitely something you can set up very easily in the freeform application and look at the how high can you go before melting becomes irreversible. No problem at all.
Fantastic. So do proteins or do samples need any kind of fluorescent label or fluorescent dye, or can this just work with just pure, tryptophan tyrosine residues?
Yes, you can totally work with the intrinsic fluorescence of a protein. 280 nanometers as the excitation LED that we're using is really, I mean, is at the maximum of those amino acids absorption behavior. So that's also why we were able to get to this really low limit of detection for fluorescence of only 25 microgram per milliliter. If your protein for some reason has very few tyrosines and tryptophans, or none, or if you have a buffer condition which quenches the protein's own fluorescence, then you can resort to a reporter dye. Cipro orange, for example, if it's a membrane protein, you might want to use CPM. We have, as long as it's excitable by 280 and or 470, we can work with it. And that flexibility of capturing the full spectrum of emission has you covered and gives you all the tools you need to characterize any protein in any formulation, really.
So this has come in from a couple of different people, so I kind of summarize the same, question down a little bit. So for the people who already have an uncle, could you give, maybe a brief couple of points that make Aunty different from uncle?
Yeah, no, of course. So the things that set Auntie apart, I mean, we've had Uncle has had a great run. We gathered a lot of information from how our users use Uncle, and we took all of these learnings and informed how we design and build Auntie. So I think we are improving on what Uncle does in every single metric. We have lower limits of detection in Auntie. We get faster faster reads in, get higher data output rates. We are able to load the samples in a plate, which is a very different and a much more streamlined way of introducing samples compared with the unis we had in Uncle. At the same time, the strengths that we had in Uncle, being the full spectrum of fluorescence, being the co-localized aggregation and fluorescence detection, and having sealed samples, all of these things that were great in Uncle, we carried over and optimized every single metric of those in Auntie. So I think it is passing. I mean, we had this one video you might remember, Ross, from internal training, where we passed the crown from Uncle over to Auntie. So there's a new queen in town, and she's here to rule it.
Fantastic, very cool, thanks. Yeah, and then also, some people have asked about this is the data comparable between, from going from an uncle to an auntie? Do you get similar results?
I would say the results will be similar. If you have a ranking of a bunch of candidates, the ranking will be the same in both instruments. If you look at the purely numerical numbers, they could be different because it is a different instrument. It uses a different sample holder. There is a different optical excitation. Uncle used 266 nanometers. Now we're using 280 nanometers, for example, for the intrinsic fluorescence. So the discrete numerical values could shift a bit, but the trends will be the same. And I think it would be very easy to prove the bridging from one instrument to the next because they are looking at the same metrics, essentially, looking at them in a different way. Aunty does it in an optimized fashion, but it's not going to be that you have to reanalyze everything you did before because it's going to be completely different. I think that bridging is going to be straightforward.
Very cool. Yeah, I know that we've done a ton of work internally on looking into that. So definitely, I think I'll ask you is if somebody is doing that sort of the sort of issues, should they reach out to us and would we be able to maybe give them some advice on how to best set that up?
Of course. Yeah, we're always
Hmm,
here for our users. So for sure.
excellent. Okay, and then is there an API license available to integrate Aunty with liquid handlers?
Yes, there is.
Cool. So I think we kind of this is kind of two questions. So I think we answered this one, but do you get fluorescence measurements uh, in the same location of the well as DLS and SLS? So that's an interesting question.
Um,
Um,
the alignment of both systems aims at the center of the well. So the answer here would be yes.
yes, but sort of one follows the other. So would there be any sort of concern that UV light would expedite aggregation?
Interesting question. I mean, I think being able to record data in Auntie as quickly as we can, if you need to give a sample a bit of time to relax. Otherwise, photo bleaching is a real problem if you emit too much light on it. But there's an easy way of entering a rest time. So you read a sample, give it a couple of seconds, however many you think that are needed, and you can read it again. For the question of triggering of aggregation of a sample by UV, there's no indication for that. The risk that you have is overstressing the opticals, overstressing the protein by overexciting it and thereby bleaching it, but that can easily be counteracted by implementing a wait time. Aggregation caused by UV I have no indication for that.
Cool. This one, what's the DLS angle?
The DLS angle is about 115 degrees.
Okay. And this was another question about the upper limit for protein concentration. This one's specifically about SLS and DLS. So upper limit for SLS and DLS that we've tested.
Yeah, we've tested 300 milligram per milliliter of an IgG. We were mostly interested in the viscosity and the loadability of that sample into the plate, and that worked. And we also got good TM and TAG data. So is this going to be the absolute upper limit? We haven't tried to take that any further because we figured 300 is a pretty good upper limit that we can stand behind for now. But by no means do I say that this is the end all number. This is just how far up we have tested it.
Sure. Okay, very cool. And is there anything like special you can do with those higher concentrations that might be useful for somebody doing protein stability studies? Some sort of specialized colloidal stability technique, for example?
Oh, okay. I was like wondering, where is this question going? I mean, if you look at colloidal stability, we look at it for dilute solutions with the diffusion interaction KD and the second variable B22. But if you're looking at especially high concentrations of proteins, let's say round about higher than 20 milligrams per milliliter, the G22, the Kirkwood-Buff integral parameter, describes you the colloidal stability in high protein concentrations better. So if you know you're going into several tens to hundreds of milligram per milliliter, you should be looking at that. But the nice thing in the colloidal stability app in Aunty is that it runs all of these three in parallel, and it's just a click of a button away from looking at those and making the decision of which is the proper metric to characterize your sample.
Cool. So this was more of another comparison to Uncle question. Fluorescence sensitivity is the question that's basically getting asked. How does Auntie's fluorescence sensitivity compare to Uncle's?
Well, so we shifted the excitation wavelength to 280 nanometers, which is closer to where the aromatics absorb, and hence we were able to halve the lower limit of detection. So 25 microgram per milliliter is where we can go. It is also a different spectrometer, which allows us to get to lower data acquisition times, which contributes to the overall speed of the system. But the major difference between the two systems is the excitation wavelength, which has the positive side effect that we can safely and stably obtain a lower limit of detection.
Okay. So would the DLS and SLS work with non-fluorescent samples?
Yes, of course. Light scattering is requiring an optical contrast between the buffer and the sample. Since water and protein have quite different refractive indices, there is enough optical contrast between them. You do not require any fluorescence to see the light scattering of your sample, unless you used an exotic combination of excipients that made the buffer the same the same refractive properties as the protein. But that is usually not the case. So you do not need fluorescence to use the DLS information. You could use if you're looking at peptides, for example, if you looked at nanoparticles, the DLS and the SLS information of those will be valid regardless of their fluorescence.
Cool. So can the plates be loaded using a multi-channel micropipette or a liquid handler?
Yes and yes. We have loaded those with a automated handler. We used an eight-armed robot, a robot with a loading head that had 8 tips in it. And we've also used a manual 8-channel, multi-channel pipetters. We've used the 12 channels as well, and the single channel works. when I saw the plate for the first time, I was like, okay, this is probably going to be not so easy to load, but trying it myself, and it really is straightforward. I am at Pep Talk at the moment, and we have a demo suite here, and we've had some people wanted to see the instrument and load it, and everybody agrees that this is fun to load because it's very satisfying to see the sample move through the quartz well.
Yes, I've definitely done my fair share of loading of these, and I can absolutely agree with you. It is quite satisfying, and it's actually also really easy to see when one of the wells is loaded versus an unloaded well.
Yes.
The refractive index difference or the refraction differences makes it
Yeah.
quite obvious. Regarding DLS and SLS, does the Aunty software automatically do the data analysis?
Regarding DLS and SLS and also fluorescence, the software automatically does the analysis. Yes, we're running algorithms to determine the TMs, the T onsets, the T ags, the T sizes, and if you're looking at the colloidal stability experiment, of course, the KDs and B22s, um, all of these. Um, all of these analyses run as you open the file after we record it. And then you as the user, of course, are invited and you should review your data and you can modify it. So for example, if you find that a TAG line is, you think, not placed where you want it to be, you can modify it and then the report would change accordingly. So yes, there is the instrument records the data and analyzes it, but you as the user, of course, have the final say and you can modify any calls that the software does. I don't think you have to, but you can.
Yeah. And this question actually was specifically asking about things like analyzing the autocorrelation functions, determining the hydrodynamic diameters, that sort of thing. That's all handled automatically as well?
Yeah, that's all handled automatically. Everything is open on display. The software uses like a chevron approach. So we have like the overview, and then we have an analysis view that's more detailed. Then we have the detailed analysis, which is even more detailed. And you have access to all the from DLS, correlograms, and you have the intensity distributions, the mass distributions, and then you have the trends. You can plot PDI over temperature, PDI over time, depending on what experiment you run. All of these things are at your control 100%. And I mean, I think it's highly transparent and you can review all of it.
Very cool. How much time does it take to measure 96 samples?
You can measure 96 samples with fluorescence, SLS, and DLS in a minute.
Okay, that's fantastic. It's always nice to hear you say that. It just makes me feel warm and fuzzy inside. So can we look at multiple runs at the same time, even if they were collected on different days?
Yes. So when I showed you the brief video about the experiment setup, I showed you that we have a selection of apps and then sub apps. Everything that is within the same app family can be, all the results that are within the same family can be opened in parallel. And it does not matter when they were recorded. So if you, for example, were analyzing an IgG with intrinsic fluorescence and in a separate experiment with reported dye fluorescence, you could open those both and compare the data straight in the software. So the recordation date is, of course, logged, but that does not limit openability. So you can open up to 4 experiments from the same app family in parallel and compare the results.
So this user remembers, and actually this is correct, that Uncle excited at 266 nanometers and 473 nanometers with laser. What was the reason for switching to a 280 nanometer LED for the Aunty?
Okay. We were looking at improving the system all around and improving the read rates, improving sensitivity, improving reliability. And all of these things were answered yes by the switch to an LED. We now have a dedicated optical system for fluorescence that we have been able to optimize for fluorescence. And we have a dedicated optical system for light scattering, which uses a laser, and we were able to optimize that for light scattering. So by separating those two systems, we were able to optimize things each in turn and get to lower limits of detection. And the switch from 266 to 280 led to helped with that greatly because we have the higher quantum yield of the 280 nanometer photons to excite fluorescence. So to answer the question briefly, we made that switch because it leads to an optimization of the system for stability characterization.
Fantastic. You talked about the excitation wavelengths already, but for the detector, what's the detector wavelength range for that fluorescence?
It's a spectrophotometer that reads the range from 250, captures the range from 250 to 750 nanometers.
So still cover it. So still has that full spectrum fluorescence that made Uncle such a great tool to work with.
Yes. It's a
Excellent.
different photometer, which is faster, so we get by with shorter acquisition times, and that leads, of course, to the overall improvement in read rates.
Cool. So this one came in. I think they're probably already familiar with Unagi, so that might be why they're answering this, or maybe already familiar with Honeybun. Um, do you need any sort of house air or compressor to run Aunty?
Yeah, interesting question. You do not. Aunty requires a power hookup, a power plug to be available, 110 to 240 volts, depending on where you are in the world. And then we have a USB cable to the computer that is recording the data, and that's it. There's nothing else required. Everything else is provided inside the instrument. So as long as you have a power outlet, that's what you need.
Okay, cool. Could someone view the raw fluorescence spectra that are obtained on Aunty at any time point?
Yes, you can.
Yes.
There is in the detail view, it is one of the screens allows you to view per acquisition point the full spectrum graph.
Okay, cool. And then, I think this is kind of really hits a more general question is, since Auntie's more is set up with a 96-volt plate format, do you think that'll be it obviously easier to automate, but do you think it'll also be a little bit easier to do high throughput experiments than,
Well, I mean, I wouldn't think it is exotic to say that 96 well plate has high throughput written all over it. Everybody who is thinking in higher throughput is thinking in formats of 96. And this way you do not have any transposition. You don't have to think, oh, A1 is here and A3 is over there. You think in plates, you have your sample lists in plates, and I think that that is the standard format to go ahead with. And I think that is going to make it a lot easier, a lot of more user friendly as well to use in that format. Because I mean, if you were to exchange a buffer, for example, in Big Tuna in a 96 well plate unfilter, you could go right over. And if you were using a stunner for your quantitation needs, you could use that same 96 format. So you know exactly, well, A1 is exchanging to that, has that concentration, that stability. So I don't think, I mean, the 96 well plate is a little bit like our next guest needs no introduction because 96 is really accepted.
Yeah, I've definitely found it to be much more of a very standard, uniform, and consistent way across, I think, a lot of the companies I've talked to. So you mentioned the use of reporter dies. Does Aunty still support AAV characterization?
Yes, it does. Aunty still supports AV characterization. You can use the Cyber Gold assay to look into the ejection of payload from your AAV capsid. You can also use it with adenovirus or a nanoparticle that has a difference in accessibility of its payload based on the temperature. That is possible as well. So again, any dye that can be excited with 280 or 470 will work. And usually with dyes, people publish the visible spectrum, so 400 to 800 or 350 to 800. But a lot of these dyes also do absorb in the UV. So the 280 nanometers can be really your joker. Even if 470 is not the greatest quantum, you'll try 280, and that is pretty likely going to work.
And then this is probably related, but rather than talking about AAVs, it's talking about membrane proteins. So can you still use CPM for stability testing? Will this product still work with membrane proteins?
Yes, absolutely. Again,
Excellent.
we've carried all we know from previous stability work over, and all of these points are retained.
Okay. So, all right. So, this one was kind of an interesting one. So, what is the longest isothermal experiment that you can run on Aunty?
The isothermal experiment can be collecting data points that are equivalent to one recording per minute for a week. I think it's
Mhm.
10,000 minutes in a week, if I remember, a little bit over 10,000. So
So,
the isothermal experiment is because of the number of data points and the size of the file that comes out of it to keep that manageable. That's what we have capped the continuous isothermal experiment at. However, I did mention briefly the out-of-the-box experiments, which means you incubate outside of Aunty. You put your sample into Aunty, you record your data, you take the sample out, incubate it externally, and just bring it in at whatever time point 2, 3, 4, 5, and so on that you want. And there you can, of course, stitch probably also up to 10,000 data points together. So depending on how much you space the individual readings, you can go much longer. For a continuous experiment, a week. For a discontinuous experiment, you are the judge.
so for automation, do you need a like special robot that we provide in order to handle the plate, or can you just use standard automation products that are already on the market?
Yeah, we tested it with a robot. As I mentioned earlier, it was an 8-channel robot that relatively widespread, one that's used in many labs. It's a relatively straightforward one to use. And so anything that is more complicated than that will also work. I do not think that there'll be any issues with that. Insert any name of a robot manufacturer here for liquid handling. These welds are spaced like the centers of a 96 well plate. The welds are big enough for the pipette tips to enter into it. Will help you develop it's easy to train the robot on it and set the right dispense speed. And this is not like we are locking you into a certain liquid handler with this. Uh, if the liquid handler can handle 96 well plates, it can handle the Aunty plate.
Okay, very cool. So we still have quite a few questions to answer. So Andre, if you've still got time, we'll keep
Yeah,
going for
let's
a little
keep
while
going.
longer.
Yes,
Okay,
let's keep going.
excellent. All right. What is the angle of the DLS detector and the SLS detector? Excuse me. What is the angle of the SLS detector? And are there multiple DLS SLS detectors? How does that whole optic system work?
Mhm. The DLS angle, the light scattering angle, I should say, is about 115 degrees. And we do, as a top measurement, we do one angle for our light scattering.
Very cool. And then, so is there a separate detector for doing the SLS measurements from the DLS measurements, or how
No,
does
we
that work?
use the information from the avalanche photodiode. We did time resolved results of the avalanche photodiode that is then going run through a correlator to get to our DLS information, and the total scattering intensity that's coming from the avalanche photodiode is our SLS signal. So we're recording those both from the same optical system and the same detector as well.
I see. So one of the users saw that during those videos that there is a barcode on the plate. Does Aunty have a barcode reader built into it?
Yes, Aunty does have a barcode reader built into it. The barcode of the plate is part of the experimental report. So you know which plate you have used. And if you use a barcode reader to index your plates or your data sets, that is something you're very welcome to use. And this is, again, a nod to people that are into automation or looking into automating their system. That barcode is going to be a unique identifier of the plate.
This is coming back to that AAV question. Can you detect RNA escape from protein capsids in viruses?
Yes, I mean,
Yeah.
you can escape, you can characterize any escape if the dye that you want to use and it matches is excitable and detectable in our optical system. So yes, you can
Yep.
certainly do that.
Yep. Cool. And yeah, we've tested that with I believe with Cyber Gold, and that worked beautifully.
Yes.
So Aunty sounds great, which is that's a nice comment. Thank you for
Thank
that.
you.
When will it be available?
We have a functioning system here at Pep Talk right now. We have demo systems that will go to our demo sites, and our FASs across the world will have those available as well. And then the instruments that are the customer orders will fill the end of this quarter.
End of the quarter. Okay, very cool. Right, so let's see here. Excuse me. Here we go. Here's one I want. Are you able to obtain PDI, intensity, mass distributions, etc., in addition to particle radius on the DLS?
Yes, you are. The DLS is a full-fledged DLS that gives you all that information. We do not report radii, though. We report diameters. So I guess the requester is more familiar with Malvern or Wyatt products. But we report diameters, PDIs. We do report their outcomes of distribution analysis, so peak-specific metrics as well, peak PDIs, peak diameters, peak diffusion parameters. So anything that you would be expecting from a regular DLS instrument will be provided by Aunty as well.
Cool. So this user is saying our group is starting to do more long-term stability studies. Can Aunty support these kinds of studies? If so, how? And can you use all three of the detection methods in those kinds of long-term studies?
Yes, you can. Yes and yes. Again, you have the option of incubating for longer periods of time at the temperature of your choosing right inside the instrument, or you could do the discontinuous out-of-the-box experiment if you want to, and you can choose if you want to record fluorescence and or SLS and or DLS. It is your choice. The sample is safely sealed in the plate. The plate can also be used for a freeze-thaw test. For example, you read it in the out-of-the-box, you put it in the freezer, thaw it again and read it again and see does it have any effect. All of these things are based on only 8 microliters of sample, and you can take a look at that long-term stability that way.
Very cool. This person asked, how long are the DLS measurements? This user is used to them taking at least a minute on a cuvette system. So, how long, basically, how long are they in Aunty, and how did we get that time down?
Yeah, we can, as the user is able to set the number of acquisitions and the duration of acquisition, the length of acquisition and the number of acquisitions. That is completely in the user. You can, if you want to do 10-second acquisitions 10 times, you are welcome to do that. Of course, if we are running DLS in the thermal gradient, and we want to read the entire plate within a minute, we don't have 100 seconds per well. We are going to do a shorter DLS. We have been able to optimize our DLS optical system by moving to a optical attenuation. Our DLS system is ultra fast, and we're able to obtain enough DLS information to get us information about the Z average diameter of our sample in the fast read of the plate. But if you wanted to run a longer acquisition of DLS, you as the user have any freedom to override the defaults. And if you were doing a standalone DLS, you can also acquire data as long as you like. It is, again, it is a fast DLS. You can get by with very short acquisitions, but if you like to record longer, that is completely your freedom to do so as well. The system will support that.
Very cool. So that was about acquisition length. Can you also change the number of acquisitions that
Yes,
the software does? Okay,
totally.
excellent. An interesting question is, does the software that comes with Aunty able to deconvolute, as a side, TMs on the thermograms, or do you have to use third-party software?
No, the software is designed to give you all the information out of the experiment that you need. So all the temperature fixed points, all the parameters, colloidal stability parameters that you determine in the experiment, and for the isothermal experiment, quite frankly, also the rate constants of the change of fluorescence, change of aggregation, that is all provided right in and from the software. You do not need any add-on software for that. The software is a standalone package. You can export data for sure, but the software is self-sufficient in as it is.
Yeah. And this one is also related to, well, that's great to hear about software. This one is also software related. This was kind of an interesting. So if somebody was using an Aunty in an upstream, and maybe with an upstream team, and then somebody else was using one for a downstream team, would they need different software implementations?
Every Aunty is provided with a computer and a license for the software. So if you have 2 Aunties, you have 2 licenses. Every license allows simultaneous installations at the customer side. So I hope that addresses the question.
I think they might be more asking about, would you need to do different analyses between them, or could you, keep maybe
Oh, I mean,
data conversation consistent between those two groups?
oh yeah, no, there is no, if you're using Aunty 358 to record a file, you can go to the computer that's connected to 359 and open it there and analyze it there. So the Aunty file is not locked to be only analyzed on the computer it was recorded, and you can move it around. Is that answering, you think, the question?
I think that's correct. Yeah, I think that's answering the question. I hope. If not, let us know. Um, can you set different save locations? So if somebody does have, I mean, I think you mentioned this briefly, but just to be more explicit, can you save things to a network drive, for example?
Yes, you can. You can set the save location. We can save, I mean, if you have your favorite experiment and you don't want to go, I mean, it's only 7 clicks to set up an experiment, but if you want to save a method, you can do that as well. Those locations are definable. The export location is also definable. So there is an easily accessible place where you can define your default locations and then return to them at every boot up of the software.
All right, fantastic. Thank you, Andre. So thanks for answering all of the questions and thanks for the great presentations. We still have many questions that are open for us. So, we don't have time necessarily to get to all of those right now, but as long as you did not submit your question anonymously, we'll be able to get them. We'll be able to get to them. So I want to thank everybody who joined us today. And I also want to thank everybody who submitted questions. That was a lot of fun, I hope. I hope Andre had fun with that too. If you do want to have a deeper conversation with our team, please get in touch with us at our email address, info@unchainedlabs.com, or you can visit our website, www.unchainedlabs.com. We'd love to connect with each and every one of you. Thanks again for attending our virtual seminar and have a great rest of your day. Andre, I will see you when you're back in the office.
Thank you so much. And thanks for all the questions. It was great fun.